Kostas will tell us the second part of the ADS-CFT correspondence basics, and he'll show us how to do computations, more or less. By the way, I saw you had a paper today, so are you going to tell us about it?
No, I can tell you tomorrow if you want to, but I wasn't planning to discuss the paper. But
I was just wondering because it's related. So
it is related, yes, but it's like handling loops. Here I'm discussing tree level.
Okay.
It's like how to do loops in the bulk and normalize.
Okay. Go ahead.
Okay, so what I will do today, I will start with a little bit of an overview of what we did yesterday, now using slides. And then I will also give an overview of what holographic renormalization is, again using slides, because I want to kind of cover the basics before we go back to use the whiteboard to actually do the computation. The last part will be a little technical, so I want to try to get across the main points before we go to technicalities. This would also give you the chance to ask me any questions about yesterday's stuff if there are any things which are unclear. So let's start with the overview. As we discussed yesterday, in ADS-CFT, we relate bulk and boundary, and bulk fields correspond to boundary operators. In particular, the energy momentum tensor corresponds to the boundary metric. If you have scalar fields with certain mass, that corresponds to scalar operators of corresponding dimension. Now, ADS-CFT has a conformal boundary, and this means that we need to impose boundary conditions there. And the fields that parameterize these boundary conditions are identified in ADS-CFT with sources for dual operators. And then the main formula in ADS-CFT is that the supergravity on-shell action as a function of these fields that parameterize boundary conditions is identified with the generating functional of CFT correlators. Now, already this tell us a few things which are important from the gravity perspective. Now, if you have a quantum field theory, in quantum field theory, the sources are always unconstrained. And this implies that the gravitational equations must admit Dirichlet boundary conditions specified by arbitrary sources. And that's a highly non-trivial statement. For example, such Dirichlet problem is not always possible. For example, in asymptotically flat spacetimes, and celestial holography has been a focus of the community the last 5 to 10 years. Now, if you look at asymptotically flat gravity does not admit such Dirichlet problem. But it turns out that the gravitational equations with a cosmological constant can be formulated in this way. So we discussed yesterday the conformal structure of ADS. We saw that if we start with ADS with global coordinates, then the metric has a second order pole at theta equals pi over 2. And because of that reason, it doesn't have a well-defined metric, however, has a well-defined conformal structure, which is defined by using this construction of starting with a defining function that has a single zero at the boundary, and then taking this limiting process. So this procedure has an ambiguity because you consider different. Yes.
So in your previous slide, you mentioned that Dirichlet problems are like solvable for the cosmological geometries with cosmological constant.
Yes.
So positive and negative, or just the ADS?
Both positive and negative. Positive and negative, the structure of the field equations near infinity. So in the case of ADS is near time-like infinity. In the case of the zeta is near space-like infinity. The structure is identical. It's one can obtain the one from the other by suitable analytic continuation. So it's not just similar, this is the same.
And one of the frequently used boundary condition for ADS is the absorbing boundary condition to study the black hole information problem. So what is the dual in the field theory side for that? Like, what would be the corresponding dual in the field theory side? What sort of sources should we expect?
Well, I would say in ADS-CFT, one should always start with Dirichlet. That's the canonical choice. And then Dirichlet doesn't mean that kind of the metric is the metric that you choose to keep fixed is arbitrary, so that can accommodate for absorbing, reflecting. If you have mixed boundary conditions, then that's kind of a new entry in ADS-CFT. Then this means that you're doing a multi-trace deformation. And I will not discuss this in lecture, but this has been understood.
Okay, thank you.
Can I ask a question? Yeah.
Yes, yep.
Is there any situation where Newman boundary condition appear in this setup as well?
Say that again. I didn't understand the question. I
There,
didn't hear the question. Yeah.
Is there any setup where Newman boundary condition appear as well on this?
You mean Neumann boundary conditions?
No, no.
Is it? Yeah. So Neumann boundary conditions you can have if you have scalars that have mass between. There is a small window of masses above the Breton-Friedman bound, and this d over 2 square minus 1, I think. There is a small window of masses where you can use Neumann boundary conditions, and you can also use mixed boundary conditions. But the generic case is that you only have Dirichlet boundary conditions.
Okay, thank you.
Okay. Any other question?
Yes, I have one question.
Yes, go ahead.
So in the next slide that you showed that 1 over cos square theta and the boundary is located at theta is equals to pi by 2.
Yes.
So it seems that there are also various values of theta at which that first term diverges. So there are all multiple boundaries are equivalent to each other. For example, that theta is equals to minus pi by 2 is also have one boundary.
I mean, in this case, there's only a single place where you have, so theta is between, you can see here, theta is between 0 and pi over 2. And in that range, only when theta is equal to pi over 2, you have a second pole. And the other thing which is important, and I don't have in the slide, is that the metric, this metric here, it has to be conformally compact. Now, time, usually we consider time as non-compact. Now, strictly speaking, this is the case not in under de Sitter, but this is in the universal cover of under de Sitter. So strictly speaking, under de Sitter has a time coordinate which is compact. It takes values in a circle. Then all of these values here. So this is a compact space. And then the only infinity is when it's theta equals pi over 2. So this is a very common mistake in the literature. People write a metric, and then they look in some way, and then they just look for the prefactors to have a pole, and ignore the fact there are infinite directions elsewhere. And then they say, okay, this is the boundary of ADS. That's not true. So to really identify the boundary of ADS, you have to write the metric as a compact part times an infinite factor, and only then the pole identifies the boundary of ADS.
Okay, thank you.
Okay, any other question? Okay, so yesterday we went through this construction to show that ADS has a well-defined conformal structure. So if it is exactly ADS, the boundary, one representative is the Einstein universe, which is conformally flat. So any other conformally flat metric, for example, the flat metric itself is as good, and that's what usually done with Poincaré coordinates. Now, if we contrast what was done in the GR literature, kind of in the 80s, so back in the 80s, people have ADS spacetimes, but they have mostly been discussing asymptotically ADS spacetimes, and they were keeping fixed a boundary metric. Now, in ADS-CFT, this is not sufficient. Then we need to generalize this setup in two different ways. First of all, we need to keep fixed a class, not a metric, because the metric is just not invariant. So you're breaking diffeomorphisms if you keep fixed a metric. And secondly, we need to understand the correspondence for a general conformal classes, not just for the conformally flat class. And we need to have unconstrained conformal classes because, as I reviewed in the first slide of this overview, the sources, the boundary conditions are sources for the dual operators, and in quantum field theory, the sources are constrained. So we need to have a general conformal class, not just some specific one that satisfies additional constraints. And this is precisely the problem that it was solved by Pfefferman and Graham in 1985. And this type of spacetimes are the asymptotically locally ADS spacetimes I reviewed yesterday. So now if we consider a specific representative of that class, then we can try to obtain a solution of Einstein equations. It turns out that problem can be solved in complete generality near the conformal boundary, and this is what was done in 1985. And then the metric takes the form given over here. So I think yesterday I used slightly different coordinates. So if you if you want to compare with yesterday, so rho is equal to z squared. Cosmological constant, then Einstein equations can be amount to algebraic equations near the boundary, and this can always be solved in complete generality. So we're not just looking in some specific solutions. This is the general solution of the asymptotic structure of the spacetime. And then the solution takes the form I indicate over here. So this G naught is the input, so it's the boundary metric we start from, the representative of the conformal structure. And then there are a number of subletting terms, and the blue pieces are uniquely determined from G naught in terms of a local formula. And we will see in a few minutes when I start going back to the whiteboard in a specific example. And
Kostas?
Yes.
Is there a distinction between even and odd dimensions with the logs?
Yes.
Okay.
Yes. So that's I think it was also, so this is only when D is even. And this guy over here is actually appears very prominently in the math literature. It's called the abstraction tensor, and it is related to the conformal anomaly in a way I will show you in a minute. And the Einstein equations only determine the trace and the divergence of this red coefficient. And this red coefficient is actually what is, in a sense, the most important coefficient from physics, because this is what determines the expectation value of the energy momentum tensor of the dual quantum field theory. Well, this is taken from another talk given for math people. It will play an important role today. Okay, so once you have the asymptotic solution, now we want to understand the divergences and the infinities. So we're going to come back to this in a few minutes, doing it on the board. Slightly different formalism, but first I want to explain how it was first done. So if you look at this expression, so we have Einstein equations. So from here, you can see that R plus 2L is just a constant. By just tracing this equation and then solving for R, which means this expression here, so this is a constant. So this expression here is just infinite because, again, the volume of space-time is infinite. So now what we do is, what we want to understand is we want to understand how to find the infinities for all possible solutions of the field equations, not for just some specific ones. And the way we do this is we take this general solution we obtain by solving Einstein equations. We put it in here, and we regulate this integral by cutting off the radial direction. And after quite a bit of work, one finds that the form of the answer is given in this bottom line. So it has a number of infinite terms as epsilon go to infinity. It has a log term in when d is even. So now to renormalize, we need to find a way to get rid of these terms. But we want to do this in a way that preserves the symmetries that we know that the theory has. So the theory has diffeomorphisms in the bulk, which corresponds to translation Poincare symmetries in the boundary. So you want to remove this by covariant counterterms. Ideally, we would want to maintain also conformal symmetry, but because of the log, this is not possible. So when d is even, there is a conformal anomaly. And actually, the most complicated part in this original way, when we did the computation not very, very long time ago, was to actually find a way to convert this into covariant counterterms. That involves starting from this asymptotic series and inverting it to find the field at the regulated surface in terms of asymptotic, to find the boundary conditions in terms of a field at the cutoff. And the method, which I will discuss in a minute, avoids this complicated step. But after you do this, so when you do this, what I just described in a couple of words, it's you find that there is a covariant counterterm action, which give here the very few terms, the first few terms. So now if you add this boundary action to the regulated one, then this limit of removing the regulator exists, and then one obtains a renormalized theory. And then once you have the renormalized theory, now you can differentiate with respect to the source to start obtaining correlators. Now this renormalized action now is not invariant under general Weyl transformations because we added these counterterms, and these counterterms do not preserve all the symmetries we started from. This is the usual story with anomalies in quantum field theory. So in particular, when you change the representative, one finds that there is an anomalous term, and at infinitesimal level, the anomaly is precisely the term that multiplies the logarithm. And this anomaly exactly matches with the anomaly we expect from ADS CFT, and we will derive that in a few minutes for d equals 2. Yes, so the anomaly itself is conformally invariant, and this is going to play a role in a minute. And this abstraction tensor, which plays an important role in mathematics, is nothing but the energy momentum tensor associated with an action, which is just the anomaly. Now we derive these counterterms by requiring that the on-shell action is infinite. So we wanted to set up ADS CFT, but it turns out actually these counterterms play an even more fundamental role. So as I discussed, the piece of data that the bulk problem and if you try to do this, then you find that these counterterms that were derived by finiteness are exactly what you need. So this boundary counterterms is what you need in order to have a well-defined variational problem. Now, if we're in odd dimensions, we just saw that in odd dimensions, you cannot keep, the theory does depend on the representative, but depends on the representative in a very specific way. So if you want to, so it's not possible to fix a conformal class because it is a conformal anomaly, but you can do the best thing next to that. Namely, you can fix a representative, but arrange such that the theory depends on the representative only through the anomaly, which itself is governed by the conformal class. And in order to do this, again, you require to add exactly the same conductors. Okay, so that's the review of yesterday's lecture and the overview of holographic renormalization. So next, I'm going to move to the board with any questions at this point.
Sorry, I'm confused. Is
Yes.
even the dimension of the boundary or the dimension of the bulk?
Even is the dimension of the bulk. So this is, yeah. So ADS 4, ADS 6, 3, 5.
Okay. Because sometimes we refer to the even and odd for the boundary.
Yes,
So
I know. It's always confusing, and it's always it's probably always good to kind of add the word bulk and boundary dimension because yeah. Any other question? Okay. Okay, so now we're going to go back to what we discussed yesterday. So yesterday we're using kind of a radial Hamiltonian formalism, and we saw that.
I have a question.
Yes.
In renormalized on selection, except the finite part, there was one more part in the action. So why we are calling that term as anomalous? Anomaly term, yeah.
This one here. Okay, oops. So the symmetry. So suppose we didn't have that term. So suppose this is not there. Then this theory would be invariant under Weyl transformations, which is the symmetry of a CFT.
Okay.
Now, at the quantum level, we see that we cannot maintain this. Now, in this case, of course, comes from infrared divergences. In the quantum field theory, comes from UV infinities. So you cannot maintain conformal transformations, but rather when you do conformal transformation, the system responds by an anomalous term.
Oh, okay. Thanks.
Any other question?
Well, can I ask you a question?
Yes, sure.
Is there any other regularization scheme, like Pauli-Villa's regularization for this kind of IR divergence in bulk?
I think for I don't think, yeah, I wouldn't think it's even possible, Pauli-Villa's, but you can do a version of dimensional regularization. It's not exactly the same as kind of standard. Well, it is in the same spirit, but it's not identical to what you would do in quantum field theory.
So
Yeah.
I was just wondering if there is any regularization scheme dependence.
Oh, they're definitely renormalization scheme dependence. So because here, when we do the subtractions, over here, so when I add the boundary action, so all of these terms are indicated here. All of these terms are infinite, but I can choose. I can choose to, when I do my subtraction, to add also a finite piece. And this finite piece encodes scheme dependence. So for instance, if you're in D = 4, you can add to this action. So ADS 5, D = 4 is again boundary dimensions. You can add to this action kind of an R square piece, for example, that has dimension 4, and it's a finite term, doesn't have infinities. And this would modify the observables. So that's exactly, it's exactly the scheme dependence one has in the quantum field theory. One discusses correlators of composite operators. So
I see. Well, so this kind of scheme dependence is in CFT is so in CFT. What does this scheme dependence correspond to?
So in a CFT, you can always add to the action a finite term that depends on sources. So usually in textbook kind of quantum field theory discussions, we discuss correlators of elementary fields. Now, for the purpose of the discussion here, we actually need the discussion of correlation functions of composite operators. Now, when you discuss correlation functions of composite operators, in order to discuss them, you can introduce sources that couple to them. And then the renormalization of composite operators involve counterterms that use only the sources. So it's not the elementary fields. So it's a classical source. So like this R square piece over here. So the metric is not dynamical on the CFT side. So it's just a source for the energy momentum tensor. And once you add this will modify the two-point function of the energy momentum tensor by a specific piece, and that specific piece is scheme dependent. So this is exact. So the scheme dependence you find in the bulk is exactly the scheme dependence you have on the CFT.
I see. Thank you so much.
Any other question? Okay, so maybe we move here, here. Okay, so yesterday we were discussing this radial Hamiltonian formulation, and we saw that Einstein equations in this formulation amount to equations that involve the extrinsic curvature. So today we'll discuss mainly d equals 2. So this time here just equal to 2. And I'm missing a page. Here it is. Okay, so what we want to do is we also discuss that morally speaking, the expectation value of the energy momentum tensor is related to the extrinsic curvature by a formula of this type, but we saw that this was infinite, and we want to find a way to normalize, and we want to connect also to what I just reviewed for you. And so this is the radial canonical momentum. And we also found that if we vary the action, then there is a piece which is on shell 0. These, which are the equations of motion, of course. Plus the canonical momentum times the variation of the corresponding field. So since we want to do, so in the IISER prescription, we use the on-shell action. So from here, we see that but as we reviewed yesterday, if you put everything together, you get infinities. So now we're going to see how to deal with those. Now, first, let me go back just one step again. So if I start with the action, so this is the action for gravity with the cosmological constant. Now, as we review, the space-time has a boundary. So if in a space with a finite boundary, not necessarily conformal boundary, a finite boundary. So then in order for the variational problem to be well defined, so if you have this is on M and there is a finite boundary, you need to add an additional term on the boundary. And This is called the Gibbons-Hawking term. Sometimes Bjork as well. So this term here is needed if you want to have a variational problem in a space with a finite boundary. And as I reviewed a few minutes ago, if you want a well-defined variational problem in a place with a conformal boundary where you kept fixed the conformal class, you would need additional terms here. And this turned out to be the same as the counter terms that we will derive in a few minutes. But let's start with this setup. Let's start just with the Gibbons-Hawking and the bulk fraction. Now, so you want this on shell. So now I'm gonna parameterize this on shell. As follows. So this L here is just a contribution from the bulk, and this term here, so let me put here, this is, we're already on the boundary. So we say when we compute this on shell, it's going to be some radial integrals coming from here. And when we do this radial integral, it would yield some quantity, which I will call lambda. And I'm going to determine this lambda in a minute. So for now, this is just parameterization. And we know this is infinite, and want to understand how is this infinite? Because we want to understand to extract the pieces that are infinite and find a way to remove them. Okay, so we want to understand the behavior of this, and we also want to understand the behavior of the dual momenta. So now I'm going to take this relation here and apply this for a very specific variation, namely dilatations, because we know that dilatations describe how things scale. So now I will apply that. So we know delta D S on shell should be pi ij delta D gamma ij. So we're going to use this relation in order to understand the infinities. Now, yesterday we discussed that asymptotically locally ADS spacetimes have the property that the radial derivative is the same thing as the dilatation operator plus subleading orders. So instead of analyzing the structure of the radial terms, I can express things in terms of how they scale with respect to dilatations. So I can introduce, so we introduce dilatation eigenfunctions. Would be functions. So this, the index here indicates what is the eigenvalue that behave in this way. Now, if you compare, so since this is the same as in the bulk, this is realized by the radial direction. So this means that AN would behave asymptotically to leading order in this fashion. So now instead of, then we can solve the field equations in a covariant fashion by expressing them in terms of eigenfunctions of the dilatation operator. Okay, now to do this, so what we have, so we need to express, to understand the behavior of this guy. So we already know the dilatation of the metric is 2 times gamma ij, and then this means that the variation of the square root of the metric is also 2 times, sorry, this should be gamma. This is true in d equals 2. And this was the reason we had infinities, because things blow up as e to the 2r.
The equal to here means 3-dimensional gravity.
Yes, yeah. So
you switch conventions.
No. I think in
beforehand
this,
you said even was the dimension of space-time, and now.
No, this was on the slide, that specific slide. I think for the rest of the talk. So this is okay. So rest. Let me put it here. So rest of talk in 3 bulk dimensions. D plus 1 equals 3. So this gamma, so here I'm using the metric I introduced yesterday, which was kind of the domain wall coordinates. So the gamma here is that gamma. Okay, so now in order to analyze the behavior, so again, also now recall from yesterday also that the explicit curvature was in Pfeffman and Graham gauge was given by this expression, and gamma ij was e to the 2r g naught ij plus e to the minus 2r g2 ij and so on. So we're interested in understanding the behavior of k, and k is the trace of the explicit curvature. So we need to understand how kij behaves. So kij is a half gamma dot, yeah, just to have the same notation with my notes. Let me put them this way. kj. So now from here, you see that this is e to the 2 rho g naught plus order e to the minus 2r from this piece. Yeah, let me make some space. So kij. So if I take the dot, I can differentiate this term. So that gives e to the time 2r g naught ij. And now the subleading term, the exponentials cancel. And then, okay, let me add the next term here as well. So then we have plus terms of order e to the minus 2r. Because the dot, when I take the derivative, it would kill this term, because I have e to the 2r, e to the 2 minus r, and it's this term which would survive. So now this is times the inverse metric, and the inverse metric is e to the minus 2r g naught ki. So now altogether, this is delta ij. So this metric has a piece that doesn't scale. So I would call this K0 ij, and has a piece that has scaling dimension 2. Because you can see from here, it has this factor here. And as we discussed, if this is the leading behavior, then this is the dimension. So K has this behavior, has a piece with C0 scaling and a piece with scaling 2. So now let's make now an expansion of lambda as well. So lambda, again, would be lambda 0 plus lambda 2. And we will see in a minute, we'll see in a few minutes, that it has to have also an anomalous piece. And I will put it here and then explain it why it's needed in a few minutes. So this minus 2r, if I write it in the z coordinates, would be like log z. So this is a logarithmic piece. This will be associated with the anomaly. Actually, this will turn out to be the anomaly in a few minutes. Okay, and then so now we have the transformation of 0 is 0. The transformation of lambda 2 would be minus 2 lambda 2, which is, this is the expected behavior. But this will also have an anomalous piece. Let me write it in different color. And then okay, so now we have all the pieces we need to work out the variation of the on-shell action. Actually, let's copy here the formula. What does it want to copy? So now from here, so we have kappa naught plus kappa 2 minus lambda naught plus lambda 2 minus 2r lambda tilde 2. And then we want to do the variation, scaling variation. Okay, so here let's organize the terms according to the dimensions. So we have two pieces that had zero scaling. And as we discussed here, where was it? We also have, so the square root of the metric has scaling dimension 2, and all the other pieces scale according to the index. So if I write here k naught plus lambda naught, and then the coefficient is 2 from the square root of gamma and then -0 because this have scaling dimension 0. And then I have the terms that go with scaling dimension 2. Oops, should have been a minus. This has a 2 from gamma, then it has a -2 because all of these terms have this -2 factor. And finally, we have the contribution, this anomalous contribution. Okay, so now you can see this terms of 0. So yeah, let's collect pieces. Okay, so that's the left-hand side. This is the left-hand side of this relation. Now we're going to work out the right-hand side. Okay, so pi was square root of gamma kappa square kij minus k gamma ij. And delta G is 2 times gamma ij. So then this gives k here because I contract k with a metric and a factor of 2 there. And now we know the expansion of this. So this has to match with what we got in the previous page. Oops. Okay, so now from here you can see this piece here definitely has a piece of dimension 2 because you have computed it earlier explicitly over here. This was this piece over there. So this means that the action had to have a piece that has a scaling 2, and that's why we needed an anomalous transformation over there. So the equations would be inconsistent if we didn't have this anomalous transformation over there. And by comparing the two, we can now equate coefficients. So then we have minus k naught, sorry, k naught And then we have K2. So then we see that now from here we can solve to find that lambda naught well, some of my signs are probably correct, but that should be the correct answer. So we find for the expansion. So we didn't really we use very little. So here we said I introduce this lambda to represent the bulk action, and we found by consistency with the scaling requires that that term takes a very specific values. So then altogether we found that the regulated action is given by this expression, and it is the pieces with k naught. It is these pieces which are infinite. So these are the pieces that we need to remove with counter terms. So what remains to be done is we remains to find a specific explicit formula for K2, and that we will do by using now Einstein equations. In particular, we will use this equation here. Okay, so now I'm inserting what I just found. So K, which is KII delta II plus K2 is 2 plus K2. So this is 2 plus K2 squared, and then minus gamma J this should be equal to, sorry, to, yeah, 2 plus R from here. And now I expand and keep terms of the right dimension. So we have 4 plus 2 K2 from this term. So this square is something of dimension 4. There's nothing in dimension 4 on the right hand side, so we're not gonna actually it's gonna cancel on its own, but I'm not gonna write it down. And then we have this times this, that gives the -2, and then this times that twice, so that gives another minus K2. So this should be equal to 2R plus 2. And now you can see the constants match. And then the rest tells us that this is equal to 1/2 R. So now from here, so now we know the counter terms, because we know what is K naught. K naught was just equal to 2, and we know what is K2, which is R. So then the counter term action.
Kostas, can you go back for a second?
Yep.
You have 2k2 minus 2k2 that cancels. So when you squared, I think you meant 4k2 on the first one, right?
4, yes.
Okay. Now I'm happy.
Yes, yeah, good. So now the quantum action is 1 over kappa squared, and then 1 minus a quarter r e to the minus r. And then from here, this is so the conformal anomaly is proportional to r, which is true in d equals 2, with a coefficient which is giving the center charge. And now if you follow, if you put all constants correctly, this should actually be correct. And you put back the ADS scale, you get that this is 3L over 2G, which is the well-known formula for the center charge of three-dimensional gravity. So that's how you get the counter term. And now once we add the counter term, then they normalize. So now the normalized Pij is just given with the terms that have the right scaling, because we have already removed the pieces that have a wrong scaling. So that will be K2 gamma ij minus K2 ij. And if you insert, so we just computed K2, it's R. K2 ij, we computed earlier. Over here. Now you insert these values here. So that gives if I put back here the ADS scale, the ADS reduce. Sorry, this is our formula. Okay. And this is the expectation value of the energy momentum tensor. So now this G2, so the analysis that we did determined the trace of G2 or the K2, but it did not determine the K2 with open indices. It just showed that this is the same, this is proportional to G2. And the full Einstein equation, the asymptotic form, leave this undetermined. And this better be the case, because these are dynamics, the full dynamics that determine what is G2, and not just the asymptotic analysis. The asymptotic analysis shows that the expectation value of the energy momentum tensor is related with this coefficient. Okay, questions? Yeah, this has been a little technical, I must say. How much time do I have, David? 15 minutes?
15, yes.
Yes, okay. Yeah, so what I want to do next, let me see, should I? Yeah, let me do one application of this formula, and then we'll discuss the two-point function of the energy momentum tensor, again, using this formula. So one application is just compute the energy of the system using the energy momentum tensor. And, as I reviewed yesterday when I started the lectures, one can use the energy momentum tensor to compute the energy and momentum. So let's start with ADS3. In global coordinates. Which now I will give yet a different set of global coordinates. And a different radial variable. Where phi is an angular coordinate. So now if you do change of coordinates from R to Z, then we go to Pfeffner-Graham coordinates. And then one finds that indeed the metric Gij is the kind of expected form, this kind of the cylinder metric. And then G2, of course, now this is a completely explicit metric. So this means G2 is fully determined. And is given by this. So now we know G0 and G2. And then we can just plug them in here to get the energy momentum tensor and then calculate the energy. So now the energy of the system would be T00 times the killing vector in this case just just the unit. And now you can use this value, insert it there, and after half a line, you get that the answer is and this is a well-known answer because this is the Casimir energy on S1, of CFT on S1, and indeed depends on the center charge of the theory. So that again confirms that this value here is the correct center charge for the dual CFT. Okay, any questions on this?
Hello.
Yes.
I have one question.
Mm-hmm.
So here, what the negative sign signifies in the front of Casimir energy on S1?
I think it is the negative sign because it's a Casimir energy. So use the Casimir energies to come with a negative sign.
That depends on dimension, but yes, in 2 dimensions it's negative.
Yeah. Okay, any other question? Okay, so finally, the final part is to discuss the 2-point function, to compute the 2-point function. So what we want to compute is we want to compute Tij point x, Tkl point y. And we already know the 1-point function, so that should be and then from here, by just using the formula we just computed, sorry. This should be KL. So if we know the 1-point function inserted in position X, if you want an insertion of the second one, we differentiate with respect to the source. And for this, we know a formula. Again, the indices are wrong. Now, when we differentiate these pieces, this give a local contribution. This is obvious. I should put here the zeros as well. This is obvious for this, but the trace of G2 is proportional to R of G0. So it's a local formula. So this are going to give, this only give contact terms. So let's for now ignore those. So this means that if we want to compute, I mean, they're computable, they're there. But the more interesting part is the actual term with the non-local term. So for the non-local term, this means that we need to understand the response of the system, the G2, the relation of G2 with G0. So that's where if we know this, then we can compute the 2-point function. Now for that one, it's exact solutions, because asymptotics just tells you it does not determine this piece. And to do a 2-point function, you just need to know how G2 relates to G0 to linear order. Since we need to know to linear order, this means it suffices to linearize the equations, then solve the linear problem and plug it back in here. So we need to linearize Einstein equations, solve them, and extract the H2. And then from there, we get the 2-point function. Okay, now a 2-dimensional CFT is usually discussed with complex coordinates. So now let me change to complex coordinates. Now the ADS metric in this 4-coordinate system is given by this metric. And now we want to introduce so we need to introduce the deformation of ADS, which will be our perturbation, which will depend on complex coordinates. So this is our perturbation. And now, so when we do this, when we introduce such deformation, what we do in the boundary, so what we do is we have an action of a CFT, and then we turn on sources for the energy momentum tension, because this is a metric. So now again, if I use complex coordinates, so the deformation of the boundary metric H0 with indices W bar would couple to the object with W bar, because what we integrate on the boundary has to have you have to match the W's and the W bars to be able to integrate. So this is the coupling. So this means now with this notation that now if I want the holomorphic part of the 2-point function, so, and I'm going to omit the constants for now. I mean, it's easy to put them back. Should be the variation of the 2 parts yeah, maybe to let me change this so I would not confuse the coordinates with the indices. So if I put z prime. Okay, so this means when I compute the linearized equations, I need to look at the piece that has components W, W bar, and I need to know the dependence of that on H naught with W bar conjugates. And the reason for that is because this is the part that couples to that metric. Okay, so that's the problem we need to solve. Now, the good thing with three-dimensional gravity is that the equations are fairly easy to analyze, and it's also easy to find the linearization. Now, we have 3 minutes, David.
Yes, we have 3 minutes.
Yeah, maybe I'm just going to give, so I'm not going to derive them. I'm just going to give you the equations. So basically, the bulk equations amount to the conservation of the energy momentum tensor and its trace. And I'm just going to list the equations we're going to need. So this is one equation. So here again, this expresses the fact that the energy momentum tensor is conserved. And now from here, I can solve this for H2. You can see here I need H2 with these indices, and this appears over here. And I can solve it. I can use kind of complex calculus. D bar. And then we have the trace equation, the trace anomaly, from an anomaly. And this determines the trace of the energy momentum tensor, which are the mixed indices of H2 in terms of the curvature, which has a number of pieces. And I see over 24, I forget. So this curvature depends on the boundary metric. Plus more terms that do not depend on this. So now from here, I can now use this equation in the conservation. Oops. And you can see I have so the two derivatives here at add to this one. So we get d3 divided by d bar, and we have a delta function. Bar of 1 over z minus z prime is proportional to delta z minus z prime, or in other words, 1 over d bar delta is the same thing as 1 over z minus z bar. And then you take 3 other derivatives.
You probably want to call it prime rather than z bar.
Yes, yes. And of course, we know that what we expect here is, so in two-dimensional CFTs, this is C over 2. And if you keep all the constants, then again, you recover what you expect. So that's how you get a 2-point function out of this. Okay, questions?
Questions?
In this way, we can calculate 2-point function only when this expansion of the metric exists, right?
Well, in this way, you can calculate 2-point functions in all cases. You can use holography. I mean, here, in a sense, the simplicity in 2 dimensions was that first, it was very easy to write the linearized equations, and secondly, it was very easy to solve them by using this 1 over d bar calculus. If you're in higher dimensions, then you would need to use kind of the Green's functions and bulk to boundary propagators. So in this case, it's more elementary than higher dimensions.
Okay.
But the method can be used really in all cases. I mean, this is the method to solve them.
So this method is applicable when we have non-ADS background as well in gravity dual.
Yeah, so if you have a space-time which is asymptotically ADS, well, this method can be used in all cases. There is holography.
Okay.
Exactly. No, I think that's full stop. There's no qualification. You can use this methods whenever you have a gauge gravity duality. So you first need to find this 1-point functions in terms of asymptotic data. And then once you have this, you solve the linearized equations around your background. And then you extract the asymptotic pieces from there, and you write off the 2-point functions. This has been applied also to non-ADS backgrounds, non-asymptotically ADS backgrounds. I mean, in all cases, the computation. I mean, this is the proper way of doing the computation. All other cases will have as assumptions. There are no assumptions here.
Okay, thanks.
Any more questions? Okay, thank you, Kostas. Let's